a lesson on using circle area to find shaded area regions. And here are two examples of problems that we're going to look at. So in each of these examples, you have the axes, which this is the y-axis and the x-axis. And same thing over here, x and y. And on the axes, you see a circle, which is centered at 0, 0 on the left here, problem 1. And you see a coordinate, 8, 6. And what that tells me is to get to that coordinate, I would have to go 8 units over and 6 units up. So I have this rectangle inside of the circle, and my goal is to find the shaded area. So one thing you need to recall is the area of a circle, and as you've learned before, the area of a circle is pi r squared. So when we look at the concept of this problem, you know, in essence, we basically want to find the area of the circle and subtract out the area of the rectangle. And then we would be left with the shaded area. So in order to do that, we have to figure out how the 8 and 6 is useful. So I know that when I look at the rectangle, that 8 and 6 are pretty useful because that tells me this is 6. And since the circle is circumscribed about the rectangle, there's some symmetry in the picture, so we also know that this is 6. And that would tell us the value here is 6. And similarly, this is 8. And this is 8. So this is 16. So I can find the area of the rectangle pretty easily. 6 times 16 is 96 square units. But to figure out the area of the circle, I need the radius. So if I take a little bit of eraser there just to clean that picture up, remember the radius you see in lots of different places in the circle. For example, I think it's really common for people to think of the radius here, but don't forget, the radius could be anywhere, and we really want to place it somewhere where it's useful. So when we think back at the 8 and the 6, since this is 8 right here, and this is 6 here, it's not so useful to think of the radius there, but it is useful to think of the radius here because we have a right triangle, and like we've seen before with right triangles, you can use Pythagorean theorem, or hopefully you know your Pythagorean triplets and already know the radius is 10, but just in case you don't, 6 squared plus 8 squared is equal to the radius squared. 6 squared is 36, 8 squared is 64. That equals 100, which is equal to the radius squared. So to find the radius, we get 10. So now that I know the radius is 10, I can find the area of the circle. So my circle area, using that formula, is 100 pi, and I'm going to subtract out my 96 for my rectangle area. And this problem doesn't have units, so we would just say the actual shaded area is 100 pi minus 96, and we'd say it's units squared, so it's squared units. So that's the shaded area. Okay, so this problem to the right is similar in that it's the same size circle. So we already know the circle area. But we'll review, in case you don't know that it's the same size circle, where that comes from. And we're going to subtract out this triangle. So, you know, in the picture, the triangle's upside down, or not really upside down, but maybe what a lot of people perceive as upside down. So it's inverted. So we have to figure out the area of the triangle instead of the area of the rectangle. So when I look back at what I have here, the 8 and the 6, the distance from here to here is 6 because it's the y value, and the distance from here to here is 8 because it's the x value. So again, we still see that right triangle in there because that's a right angle, and so that's 10. So the base of our triangle is 16, but we have to figure out the height of the triangle. And the height not only involves the 6, but it also involves this distance here is the exact same as this distance here because it's still the radius. So the height of the triangle is the 10 plus the 6, which is 16. Because it's the distance from here to here, from the bottom of that vertex of the triangle. So the height is 16. And the radius of the circle is still 10. So the shaded area this is 100 pi. So it's 100 pi minus half the base times the height, because it's a triangle. So 100 pi minus 8 times 16, because half of 16 is 8, which is 100 pi minus 8 times 16, which, if you think of 8 times 16, it's just 80 and 48, because 8 times 10 is 80, and 8 times 6 is 48, so 128. So the final answer is 100 pi minus 128 square units. That's your shaded area. So just kind of taking a step back, problems are very similar. They use the same right triangle. Sort of the key to that problem is being able to figure out the radius of the circle given a coordinate. The next type of shaded area problem also involves circle area. So we need to keep in mind what circle area is, but it's also a different look of a problem, because this sector, that's called the sector, it's just like a slice of pi. So it's part of a circle. So we're going to use ratio and proportion. So remember, the area of the whole circle, of the entire circle, is 400 pi from the formula pi r squared. So the sector area, you can think of it as sector to circle is equal to degrees over 360. So in looking at this problem here, I'm trying to find the area of the shaded sector, so I'm going to call that A. A compares to the circle area, 400 pi, as the degrees, 45, compares to 360. And I would encourage you to reduce. 45 goes into 360 equally, because it goes into 90 twice, and 90 goes into 360 4 times, so that's a 1/8 ratio. So we're really going to set that equal to A over 400 pi. So to solve for A, I'm just going to cross multiply and say 400 pi divided by 8. And then 8 goes into 40 5 times, so it goes into 450 times. So our final answer is 50 pi. So the shaded area is equal to 50 pi centimeters squared. So that's just finding the area of a sector. It's just a simple ratio and proportion problem. So if I want this little piece, that's called the segment. So a segment of a circle is just kind of like that, kind of like the crust of a pizza. So to find a segment, it's always associated with the triangle, so we just want to take that sector and subtract out. Basically, you're going to subtract out this triangle, and then you would be left with this segment that is right here. So that's the strategy that I'm going to use to find this shaded area. So from this picture, I see that this is 6, and it's also the radius. So this is 6. This is a right angle, which tells me that this is 1/4 of the area of the circle. And I'm going to subtract out 1/2 base times height for the triangle area. So let me try that one more time here. So this is 1/4 of the circle, and you're going to subtract out the triangle. And so this is 6, so it's 1/4 of 36 pi, because remember the area of a circle is pi times r squared, and that's pi times 6 times 6, which is 36 pi. And then I'm going to subtract the area of the triangle, which is half of 6 1/2 of 6 times 6. So this is 9 pi minus 18. That's my shaded area. So we would say it's 9 pi minus 18 centimeters squared. So just in, looking at the different problems, they both pages involve circle area, and then both pages involve symbol shapes like rectangles and triangles. That's kind of the gist of beginning shaded area problems with circles. So this last one, again, it's a little bit different because it's giving you the shaded area and you have to find the angle. So we still need to know circle area. And then the other thing is it's helpful to think of shaded area, in this case, is a sector. Which is that slice of pie. And so because of that, we could use a ratio and proportion. We could do sector over circle is equal to degrees over 360. This time I have the sector, so 14 pi over pi times 36, because r is 36, r is 6. So pi r squared equals 36 pi. And I'm looking for degrees, but I know the total degrees in a circle is 360. So definitely want to simplify. And then when we multiply, we get 14 times 360 divided by that leftover 36. So 36 cancels into there 10 times. This is what x is equal to. So 140 degrees is equal to x. So that's kind of like a going backwards problem. So we learned that this is 140. All right, that's just kind of a summary of how to do shaded area problems in a circle.